Hi, in this video, we want to take a look at the method of moments. Okay, the method of moments is a technique for estimating the parameters of a probability distribution. So I've got some data coming in. I believe that my data is independent, identically distributed, all from the same distribution. Okay, so I've got data, and I've got an idea of which distribution it's coming from. So now all I need to do is just estimate the parameters of that distribution. All right, so what I want to do is I want to take my data and figure out what's a reasonable value for those parameter estimates. Okay, so what we're going to do is we're going to take the first moment from probability theory, and we're going to set it equal to an estimate that corresponds to it, and then which will be the sample mean. Now, I'll also go to the second moment, so the expected value of x squared, and then I'll take the sum of my observations squared divided by n, so it's the average of the squared values, set them equal to each other. Okay. And if I need to keep going, I'll take the expected value of x cubed and set that equal to the average of my cubed values. And I keep on doing this until I get all the parameters I need. So if I have a very complicated distribution to work with, let's say maybe 5 different parameters in there, which is possible, then I would be using 5 different equations. And this would be a system of equations. I would have to just go through and solve it. All right, so what we're going to do is, this is our fundamental equations that we're going to set the kth moment of the random variable. Well, I'm going to take the average of my data to the power of k and then set them equal to each other. So here, this is my population variable to the power of k, setting it equal to my sample to the power of k average. All right, so the first expected value is set equal to the sample average. So population average equal to sample average. That's very intuitive. Then the second moment, the expected value of x squared is set equal to the average of my squared data. Then the expected value of x cubed is set equal to the average of my cubed data. And I keep on going down until I get enough equations to solve this. And we want the least powers possible, and we want the fewest equations possible to achieve this. Okay, so like if there's only one parameter and the expected value and sample average satisfies figuring it out, I'm not going to use the second moment, third moment, and so on. All right, so there's advantages and disadvantages with this. There's a lot of disadvantages, but this is the major, huge advantage of this is mathematically, this is very simple compared to other techniques. Now, if you're not comfortable with systems of equations, this looks like a lot, but I promise you, this is pretty quick and easy compared to some alternatives. All right, so some advantages of the method of moments is that mathematically, this is simple compared to other techniques that we can be using. This is well established. Okay, so this goes back to Carl Pearson in the late 1800s. This is well known, well established. This is probably not the favored one. Maximum likelihood estimate is probably the most popular, but this is probably number 2 overall. Now, something that's nice about this is that this almost always produces an estimate of some form. Now, with other techniques, mathematically, it might not work out, or computationally, I might have problems just getting the computer to compute it. You know, we can get some very, very complicated estimates if we start going through, you know, through different methods. And method of moments, because it's so much simpler, is almost always going to give me something. Now, here, under very weak assumptions, method of moments gives us a consistent estimator. This means that basically I get overall an accurate estimate of what I'm attempting to estimate. All right, so that's a huge advantage. Now, one use of method of moments is that when I'm working on, when I'm using actually a more complicated estimate, let's say maximum likelihood estimator, well, it can be complicated on how we get to the actual value of the estimate. And a lot of times there'll be an iterative method. Method of moments frequently gives us our initial starting point in the iterative process. And method of moments tends to work when other techniques fail. All right, so there's some disadvantages. All right, first and foremost, the big one is this can give you values outside the possible range of parameters. So basically this is saying, if I know I have a parameter that has to be positive, it's possible for me to get negative value. But this is very rare for larger samples. It will come up with smaller samples more frequently, and also the samples tend to be more extreme in the cases where you'll get something absurd. Frequently, we're going to get a biased estimator from method of moments. That is to say that the expected value of my estimate is not equal to the actual value I'm looking for. So up here, this accuracy is saying that if I have a large value of n, my estimate is going to be more than likely very close to the value I'm attempting to estimate. But that's within an error tolerance. So here, this is saying that the error tolerance will never really be exactly 0 in terms of an expectation. Frequently, method of moments will have larger variances than other options. And frequently, it will not be an efficient estimator. So efficient estimators are unbiased and they have minimum variance. So frequently, we're not going to have an efficient estimator. Now, method of moments may or may not give us sufficient statistics. Sufficient statistics are saying that I'm using all of my information, and if I was to lose a data point, I would lose information on the goal that I'm attempting. So sufficient is just saying that I'm using everything, and it's not possible to take advantage of my data to any fuller extent. All right, so let's work on some examples. Let's do, but I'm going to do things just a little bit differently than actual method of moments. What I'm going to do, instead of doing method of moments as I presented a moment ago, I'm going to say that the variance is what we're going to work with. So I'm going to take the variance, I'm going to set it equal to the sample variance. All right, and so expected value of x equals x bar. That's just like what I have up top in the documentation. But instead of the second moment, I'm using the variance. Why am I doing this? Well, it's so easy to get the sample variance, and the equations for variances are like more readily available and more familiar than actual moments. So I think this is a better choice in actual application. All right, so let's do an example with the Bernoulli distribution. All right, the Bernoulli distribution, it's probability P of being heads, probability 1 minus P of being tails. I have one parameter that is P. Okay, well, I know that the expected value of X is equal to P. And so I'm going to replace the expected value with the sample average, and I set them equal to each other. And that's how I get my estimate of P. Okay, so let's do an example. Okay, let's say I have this Bernoulli data, use a random number generator for it, and I have the data, but I don't know what P is. I want to estimate it. Okay, well, let's go ahead and let's just take the average. I'm going to take the sample average. I set equal to P hat. All right, well, there's the average. So here, this is my estimate of P. Okay. So let's take a look. Let's see if this makes sense. So first and foremost, I'm going to take a histogram of my data, and then I'm going to plot the distribution that I'm estimating with. If they look similar to each other, I'm convinced that I made a good call. So here is the histogram of my data. Now I look at the bar plot that arises from from this p-value being applied to the Bernoulli distribution. And I look at these, and height-wise, they look proportionally about the same as what I had. So I'm feeling good about this. I think this is a good estimate of P given my data. Now remember, it's only an estimate. I don't actually know what P is. Remember, whenever I'm using data, I don't actually know what's going on. Let's look at the geometric distribution. So now it's going to be a little bit more interesting. I know that the expected value is equal to 1 minus p over p. And remember, there's two presentations of geometric distribution. I'm using the one that includes 0. So we're counting the number of failures before our first success. Okay, well, I'm going to take x bar. I said equal to 1 minus p over p. And you notice I have estimate for p hat. Well, if I do a little bit of college algebra, I can see that p hat is equal to 1 over x bar plus 1. Okay, and so now let's run through an example. Let's actually do this. So here is my data. Now here is the average of my data. So here, this is x bar. So it's just a little bit less than 4. So now, if I apply the formula I got here, my estimate is going to be 1 over 1 plus the sample average. Boom, we've got it. So it's close to 0.21. All right, so now let's look at the histogram and the distribution to see, do these line up? Am I convinced I made a good choice? All right, here's my histogram. All right, and now if I take my estimated p-value, which is right here in the distribution generation, I can see that this curve going down. Now, do these match up? Well, this is a relatively small sample size, so I'm convinced that it's okay. It's a little bit bumpy, but remember, I only have so many observations to work with, so I'm convinced. If I have a larger sample size, then my histograms tend to look smoother, and it'll be easier for me to tell, do I have a good estimate or not? All right, now let's kick it up a notch again. Let's look at the gamma distribution. All right, so for the gamma distribution, expected value is alpha times beta, and the variance is alpha times beta squared. Okay, so I have these two equations. So what I'm going to do, I'm going to replace the expected value of x with the sample average. I'm going to replace the variance of x with the sample variance, and I set them equal to these equations using estimates. Okay, well, if I sit down, do a little bit of mathematics, I can see that alpha hat is equal to x bar squared divided by sample variance, and beta hat is equal to sample variance divided by x bar. Okay, so now let's execute. Let's do this. So here is my data I have to work with. Here is the mean. All right, so it's close to 50. Okay. What's my sample variance? Okay, not too far from 500. All right, well, so if this is 50 and this is about 500, I know that beta is going to be around 10. And so that means that alpha will be around 5. Okay, but let's see what happens. All right, so to estimate alpha, our shape parameter, I take the average squared divided by the variance of the data, and I get about 5. Okay. Now, to estimate beta, I'm going to take the variance of the sample and divide by the mean of the sample. Let's see what we get. Oh, we get something just under 10. Okay, that's looking pretty good. So now let's check to see, does the histogram of my data look like the distribution that I'm going to use to estimate with? All right, well, here I've got my gamma distribution. Looks like I've got a little bit of bump right there. And that potentially could be a gamma. Now let's take a look at the bar plot. Now here, this is a much more complete representation of the distribution than what I have up here. So I have to make a decision, do these match up well enough to proceed? I feel like it's okay. I feel like it's good. There is a difference between the histogram and the density, but that's really, from this point of view, that could be explained by just having a small sample size. All right, well, that's all I've got for you. Take care and goodbye.